right, hello everybody, and I think we can continue now. I hope you had a nice break, and we are going to continue to explore finite difference methods for discretizing partial differential equations, such as Navier-Stokes. Because I am mainly a science educator, so my focus is mainly on teaching and how to present the usefulness of numerical methods and programming. As I'm teaching fluid mechanics in Norway, only recently they have become a greater focus on programming and using numerics in education. And so lots of our students do not have much experience in programming. And so there's always a question which language to teach first. And as you're probably familiar with, many big educational institutions are using MATLAB. But in a situation which is not unique to Norway, I guess, when our students are graduating and seeking employment, many of them will be working in small or medium-sized enterprises. At such workplaces, they usually don't have MATLAB because it's a very costly program to install. So lots of students will be faced with having to use open source programming languages. So that's why I am including a little bit about Python resources in this lecture. So I hope you will find it useful, and probably many of you know about Python already. Somebody have learned only MATLAB. Some of you have done C or C++, or maybe some of us are grown up enough to have seen Fortran, as I have done. But what is being told here together is useful or translatable to any language. So to sum up, we have introduced predictor and corrector methods. These methods are called explicit, and it was because when we compute next time step, like for example written in this formula here, it is based on the previous step. But such methods are very simple. It's essentially, it boils down to this Euler method, which we are, when we're computing next step, by multiplying the first order derivative with the time step and advanced. And it generates big mistakes, big errors. So to kind of improve the performance of such a method, we are introducing predictor and corrector steps. The first step is predictor, is like Euler. We are marching one step delta t, multiplying with first order derivative, as you see. But using forward differences, but this is not good enough. So we introducing this corrector step, which uses these quantities computed in predictor step. In our case here, it is density and velocities. But now we are putting them in backwards differential scheme, which you recognize as these first order derivatives discretized in backward steps. You recognize them by seeing those I and j minus 1. So now we have values obtained from the two steps, the predictor and the corrector values for derivative. And so we're doing the simplest possible thing we can do is to take a simple average. So now we have obtained a value for derivative, which is somehow an improvement because it's an average of backwards and forwards. And finally, we are ready to advance to the next step with this same Euler type scheme. Of course, it's not the whole story. You can do much more than only utilizing two steps. Methods such as Runge-Kutta, for example, using 4 steps with 4 weighted averages, averaged derivatives. But it would be outside of this scope, and computing these 4 steps would be very cumbersome to code for Navier-Stokes equations. So here I want to present how can we use this explicit Mccormack scheme in on a general equation of a type like Navier-Stokes, which combines derivative with respect to time and partial derivatives, mixed partial derivatives with respect to spatial coordinates. So let us look at two-dimensional compressible flow. And for that, we need to find density and velocity components for this. We need equations for the Navier-Stokes, the two components. You recognize it as x and y direction. So again, this is our old dear Newton's second law, which we remember we're using this humble down-to-earth approach. We always look at what it actually represents. This is mass times acceleration equals to the sum of forces that act in x direction, the same in y direction. So we have two force equations, and then another one, which is the continuity equation, which also have to be satisfied. But because we are having a compressible flow, we cannot remove this density. So we have to drag it around with us through all equations and discretize it. And we also have an equation of state for connection between density and pressure, and c is the speed of sound in this medium. So how do we make a Mccormack scheme, explicit scheme, which we have now seen the basic idea? For the general equation of this type, where we have derivative of this quantity with respect to time and with respect to x and y, because we have like density multiplied with a component. So it can be formulated in a general way. Predictor step and corrector step, where we are, I hope you can recognize this first order derivatives forward in x, forward in y for predictor step, when we're taking the forward steps in first order derivatives, and for corrector step, where we are evaluating using backwards difference. You recognize it by seeing this minus ones. Now we're taking a step backwards, and the quantities we have computed in the previous steps. Here they are marked with star. So first we're computing U star and E star and F star, representing densities and velocities with predictor step, and then we are putting them into a backward scheme to compute them with corrector step, which help us to increase accuracy. But of course, there are many ways to do it. This is the simplest. And actually, such schemes are very susceptible. They have a very profound weakness. They are very sensitive to the choice of steps in x and y and time. So very sensitive, and a wrong choice of step size may lead to complete divergence of solution. So we can say, as been noticed in a discussion in a previous hour before break, this is the price we pay for simplicity. We're only computing one step based on previous instead of solving equations like we do in implicit methods when several time steps are dependent on each other. Here is only one at a time. And this simplicity, because of course, will lead to some trade-offs. Okay. So to sum it up, for predictor step, we compute predicted values. For our quantities, discretizing these three equations: continuity and momentum. Density times velocity is momentum. divided per mass. So we have to discretize them on predicted quantities, which we are marking with star. This will be computed based on previous step. And they are, of course, not final because we need to go to the next step. So how will this look in discretizing? And these expressions, I had to check them several times. They are, to avoid mistakes, these are taken directly from this book I mentioned for you, Fluid Mechanics by Kundu, Cohen, and Dowling. So we can only hope that they are correct. They seem very correct because you can easily recognize when you see these indices. Here you recognize the forward scheme and in X and forward scheme in Y to find the predicted value of density. This is from a rearranged continuity equation, which we have seen in the previous session. And now we are attacking this momentum in X direction and discretize it. I will not move back to show this equation again, but you will have them after this lecture. You can have all these notes. And we are discretizing it again with using for this direct and for the mixed partial derivatives. Right now, it may look like an abracadabra, but if you look at the indices, you may recognize the derivative schemes in forward and backward in X and Y, the central difference for the second derivative, and you will recognize this mixed partial derivatives term with the 4 terms. All those computational molecules that we have been presented, they're all there with appropriate indices at step n, time step n. I've forgotten to tell you that we didn't note it in this upper index, but I guess it's quite obvious that we need to do this for every time step. And exactly the same procedure, only for the Y component of velocity, which we're repeating here. Density times velocity is a measure of moment. There is a typo here, it's in the Y direction. As you can see, it's V. And we are again churning through the same machinery with discretizing with all those schemes presented, backward, forward, central, and this mixed one, which involves 4 points. And this is only predictor step. So it's the half of our job actually, which have to be repeated at every time step. So now that we have made the predictor step, we need to move further and produce the corrector step. So the corrected values for the same time step, t plus delta t, or tn plus 1, the next step, we again discretize all 3 equations, but now they will be evaluated at different points. So we will need another set of arrays to store these values when we will be writing our code. And all predicted values at this step, they will be marked with n plus 1, and they are computed based on those star values. And then they will be copied to become the new step n, and so on and so forth through all time steps. So how we will now look for corrector step? It's the same equations. So the mathematical form of the equations, the same factors, but with 2 important differences. Now you see we are evaluating at backward and with star quantities, which are being predicted in the predictor step. exactly the same. You can see these main differences. The star and indices change from forward to backward. So it's a piece of code that can be reused, but they have to be really careful. It's so easy that the minus changes to plus, and then can be hard to debug. But it's the same pattern that is repeating, only backward step. In X direction and in Y direction, same procedure. So now we have completed predictor step and corrector step. But we also need to put all those constants, and they have their special values, which are defined through the size of the time steps. The size of the time step is a big problem to determine. And this is what they call the Achilles heel of these methods, is they are very sensitive to correct choice of such constants. And if you only going forward with trying and failure, then it quite hard to find the area where the solution is stable. But it can be, you can produce relations between this, and it will also vary from equation to equation. For simple equations, there is something called courant number, and gives the relation between time step and step in X or in spatial direction. And so there is an easy relation between divided by step in X should be less than 1. And but it follows from the structure of the equation itself. For more complicated equations, you cannot, it's not sufficient. It has to be, this relation have to be deduced from the structure of equation to be sure. So it's not so easy to fulfill them. And for this particular equation, they have been done quite a lot of work to actually find the constraints on time step. And it was, as you can see, it is not an easy relationship. It's quite complicated. You have a semi-empirical formula, which was not completely analytically developed. They had to do a little bit empirical experiments, numerical experiments, to formulate this. So you see, it has a complicated dependency on X, on delta X and delta Y. And also related to the numerical Reynolds number, grid Reynolds number, which is related to quantities in the equation itself. Minimum mesh Reynolds number called it. And an empirical factor, sigma, which is around 0.9. So it's not straightforward how to find this time step. So if it's not fulfilled, you're basically not guaranteed to get a convergent result for this. So there is an example how to solve such a two-dimensional Navier-Stokes on a situation which can be described with a quadratic box in 2D with a movable lid. And the lid has a constant velocity in X direction. Let's call it U. So that means that the particles which are in contact with this upper lid will have this velocity because of the non-slip condition. And velocity will be 0 otherwise, because again, because of this non-slip condition. And V, the velocity in Y direction, is 0 on a whole boundary. So that means that we have to do a little bit more, because as we see when in solving equations, simply discretizing it, it is the most important job, but it's not the whole story, because we need to handle the boundary conditions. Because when we have to solve it and start the iterations, we need some starting values. And we need to describe the situation as close to physical conditions we want to model. So again, we need to treat these boundary conditions in a special way. First, we have to see how this continuity equation behaves on the boundary. What is easy there is we don't have any velocity in y direction. Therefore, v can be put to 0. So we have a little bit simplified continuity. So we will have to adjust our predictor corrector scheme for the boundary values. It becomes a little bit simplified too. It becomes a second order scheme. And we can use this simplified expression on the boundaries. And then we can look at the left and right wall. Why do we need to do it separately? Because on left wall, we have all x values equals to 0, and the y values vary from 0 to max. And on the right wall, again, x is constant, is equals to d is the size of this box enclosure, and y varies. So we have to simplify a little bit our predictor and corrector steps only for the boundaries. So they have to be implemented separately for every time step. So our predictor and corrector become like this. And we have to adjust our indices because we are at the boundary of the system. We don't have neighboring points to the left, and we don't have any more neighboring points to the right. Therefore, these indices become adjusted with 1. So we have I plus 2 instead. And similarly here, we have to adjust indices because we cannot cross the boundary. We don't have any neighbors to the right of where we are. So we have to take this into account. So what about the top and bottom? Again, we need to do a separate computation for taking into account these boundary values. On the bottom or front, and depends on how you interpret this situation, then we will have y equals to 0, and x runs through all values of the boundary. And so we are again adjusting our scheme for density, predictor, and corrector step. And finally, on the upper wall, where we have constant value for y's equals to d, then again a new expression which takes into account how far we can go in the y direction. So this is something that has to be done at every time step. So one can see that even with a relatively simple scheme of Mccormack with only two steps and simple average, it's quite a cumbersome piece of code, a lot of coding to do. And we are still not done yet. We have done, now we have to kind of sum up what will go on for every step. Velocities are computed by dividing momentum by density. This is what we're going to do to find velocities. And here is to sum up all the predictor steps in one. So this is what's going to happen in the first step, initializing velocities, making a prediction for how density and momentum will be, computing new velocity, and corrector step, where we are using these predicted values in backward differences, and remembering all those constants, which are all dependent on the step size in x, y, and time. So this is the procedure which have to be done at one step. Now, how do we implement such a thing? And as I told you already, my focus is mainly that of a physics educator, and trying to convey the usefulness of these methods and why we need programming and numerical methods and all. Later today, you are going to do much more advanced methods, such as finite volume, finite elements methods, where you really going to use big advanced packages where you can handle any types of geometries. You can imagine that if it's hard enough to discretize a simple rectangular grid with equally spaced elements in the grid, then in real life, it is not efficient enough. Usually, you will be interested in grids that can change sizes, like the grid points becoming denser in areas with complicated geometry, where you want to represent the flow better, and letting the grid size be larger where in places where nothing interesting is happening. So you can ask, why do we need this finite element methods? And I would advocate like two sides with them, which I think can be important, even though these methods may be considered a little bit old-fashioned and they have all those weaknesses associated with sensitivity to time step. One is, of course, that when you are using packages such as star CCM+, for example, which you're going to use a lot, all these computational details, details about physics, about equations and the structure of equations, they are hidden into a black box. And it's not so easy to get a feeling of what is going on. And even if you could look into this black box, sometimes it will be not so clear what's actually going on, because it's such a specialized discipline to write numerical codes. Then it's not easy to see the physics behind it. Here, you can still recognize the structure of equation in the expressions themselves. So from educational point of view, I would definitely say that the finite element methods are much better to convey what's happening as what is the physics in fluid mechanics, and explain how what these equations are doing. When it comes to publications and how many research articles are being published with finite element methods, you will not find them as, maybe not as much new breakthroughs are being done with them. But if you search for example, for Navier-Stokes with Mccormack schemes, you still get quite a few research articles actually doing it. So as a fundamental research, this is not unfashioned in any way, so it is still something you will do. So it's not completely useless to review some of these methods. If you want to have some sources on where these relations and equations come through, so as I have already suggested you fluid mechanics books, there are several. The best one I found was the Kondo, Cohen, and Dowling. This is where the relations for discretizing for McCormack scheme came through. And also if you are interested in numerical methods per se, not necessarily related to fluid mechanics, then there is a very good online digital compendium from also from Norway, from NTNU, by Kolstø, Hellevik, and Sønstebø, which is a very good for applied finite difference methods and other numerical methods, numerical recipes, and which is for actually universal for many languages. And because I have wanted to talk a little bit about Python today, I recommend especially this fantastic online tutorial made by Lorena Barba Group, which is called CFD Python 12 Steps to Navier-Stokes. Why Python? As I told you already, that it's open source and free of charge language, which anyone can use, and some universities are already taking them into their curriculum. For those who are used with MATLAB and have learned MATLAB, it's a little bit, it's a little step further to learn Python. There are lots of things which are very, very similar, but at the same time, you have some things which are very strange, especially when it comes to handling of arrays and matrices and loops, as I can show you a few examples of, which is takes a little bit getting used to. If you want to start learning Python, if you have not done it before, then I would suggest to use something called Jupyter Workbook. It's an online programming environment that helped me a lot when I wanted to find out how to translate from MATLAB, which I have been teaching, into Python. And when you do a random search and start asking people how do you start with Python, then most of people will recommend you something like this. You don't need to actually download anything. You only start working in a workbook online, and this build up with cells. Each individual cell, like here, is a tiny independent piece of code or script, and then can be run independently. So you are free to experimenting with different commands, different pieces of code, and you can very fast attain basic knowledge. When it comes to tutorials, from my experience, there are so many that it's really hard to choose which one to follow. And it also depends very much on what kind of background you have. Are you fluent in C, in C++, in object-oriented programming? Maybe you are old school and used to Fortran, or maybe you are a MATLAB user. So it will be very individual which approach is easy. So that one, I will just say, try different ones until you find which is easy. What I have noticed as a relatively new Python user, what we want to program is not necessarily the view of people writing tutorials, because because I'm teaching fluid mechanics, I want to know how to make loops and matrices to do these numerical methods, right? So I think, oh, I can do as MATLAB. And then I discovered that Python doesn't really have arrays. It has lists and lists of lists. So what you really want to know is how to use NumPy. This NumPy, you see that every numerical code starts with import NumPy as NP. It's actually a numerical Python package, which is developed especially for doing numerics, as the name suggests. So there you find the array structure, which we all expect should be in every language, but Python, it's actually lists. So you need this, import this NumPy and actually learn about how NumPy works. So instead of just searching for Python tutorial, I suggest you search for NumPy directly, and you will find a range of useful resources to work through NumPy. So you can start experiment with this NumPy array structure. It is deceivingly similar to MATLAB. At the first glance, you almost use it as you would use a MATLAB arrays or vectors, as they're called. So this is very, you think it's very easy, but then you discover that there are different ways to implement loops, and it takes some to get to use some learning to use it. Another useful thing I have experienced was worth the time. Where to deposit files. If you want to share files, for example, with your students, I know that people here at this summer school have very diverse backgrounds. So most of you maybe worked as scientists, as engineers, and maybe some of you working at universities who will be teaching someday, or maybe already teaching courses in, for example, fluid mechanics or numerics and so on. And if you want to know how to easily share files, I can recommend you file repository GitHub. It is also free of charge. And as far as I understand, if you register to it, you can easily upload your files and share your files with other users and search for different numerical codes, which I had some useful applications for. So the Python resources I have mentioned for you, I have put on my directory called Python Numerics. I'm BPO Virgin, so you can share it and access it if you like. So if you are interested, we can take a look at some of those resources. A little second. What I'm talking about is this very useful resource which I have been using when learning myself Python. It was this Jupyter workbook. I can guess you also can recommend other similar resources. And here I have collected some of examples which are very useful to learn basic fluid dynamics equations, which are taken mostly from some textbooks and from this resource which I told you about, the CFD Python, 2 steps to Navier-Stokes. Here you can search for it and find it very easily. I will not go through this. This is just my recommendation, which you can do. And for me personally, it was a very good and practical way into learning Python and applied to basic equations of fluid mechanics. You start with convection and diffusion equations and doing these basic schemes, and then you are gradually, step by step, proceeding towards Navier-Stokes equation. So this is something I would definitely recommend you doing if you have time for this. For a second. And just to get back to my my page. Too many windows open.
Okay.
Here, finally, I hope you can see it. So to work through all those examples, I will leave it for your spare time. And really, I have found them extremely useful because they start very gradually with taking discretization step by step, just as those schemes were presented today earlier. One step at a time was forwards, backwards difference applied at first and second order derivatives. And what is such a great thing about this programming environment, as I told you, don't need to install anything. You can run every cell, this green border around indicates that it's a cell, it's a separate script. And here you can, it runs independently. So it's not dependent on what you have done in the previous cell. So each one is a separate code where you can learn step by step how to do Python scripts, how to do numerics, which packages you need to do. So I absolutely recommend you to work through these 12 steps to Navier-Stokes first, which I showed you previously, and follow the steps on your own, and writing this line for line and trying to understand what every line is doing. Now, what I wanted to tell you about this special peculiarity of Python compared to, for example, MATLAB. For me, it's easier to compare everything to MATLAB because that's what we're doing in our course in Bergen. When you are making an array, you think, oh, it's simply like MATLAB, and I can access array elements using indices. And of course, you can do it. Here, for example, when we are doing an example with linear convection, if you want to do it yourself, as I told you, you can find it on this GitHub file depository. And all files lying there should be correct and without bugs. So you can also copy them to your own Jupyter workbook or your own Python installation on your computer and run them. But I am doing it here in the browser, so I don't have to open multiple windows, many enough already. So lots of functions are very much like in MATLAB, but they have to be imported as packages. In order to use array, you need the NumPy. In order to do plots, you need to import packages, libraries, matplotlib, importing package pyplot. So otherwise, you cannot use it. So they're not built in like in MATLAB. Of course, when you want to do loops, that's the first thing you can do when you're doing a numerical methods. You want to know, how can I do a loop through all elements into an array? They can be written like this, very much like MATLAB, with for and the indice, which goes in a range, which nt is then the number of time step. And inside you can have double loops, and inside the loop, you can write it as you would expect in any programming languages. The only difference is what kind of parentheses you have, rectangular or curved parentheses. So here it's almost like you're seeing MATLAB, almost. well, except this difference that you don't have any end sentences. So all which is inside the loop is controlled by the inset, how many times you have to push space. Luckily for you, this is a mistake you do only very few times before you learn it, and not place things inside loops when they don't have to. But it can be a feature which is hard to use, to get used to for those who are used to writing end or parentheses, because there are no delimiters to tell you explicitly that the loop is finished. So you only have to do this in lines. The code helps you by changing color when you write in them. So it's red until it stands on the proper position. So you can do that. When you run it by pushing the run button, and it produces the output. And you are happy because you have learned the background. But those of you who have done lots of Python programming before, you will say that this is a very stupid way to do this. And this is because such a direct notation to access the vector elements, array elements, is very inefficient, because again, it's a package which is written to utilize indices in more direct way. And it can be done if we drop the loops, and the loop itself will be incorporated into the structure. Can I find you an example how it is done? But I think in the beginning, when you're first learning to use it, it's okay to stick with this inefficient notation. But how can we do it if we want to speed up the code, which is recommended to do? Here is another example of two-dimensional convection. And here, instead of looping through x and y values, we are using a structure inside the vector parentheses. So instead of loop, we have only one loop. It's over time, it has to be, but no two loops over x and y. So instead, I'm using the notation which tells how far these indices run. So you kind of incorporating the loop into the vector notation itself. And this is what I found most strange and maybe uncomfortable with Python compared with MATLAB or C, is this notation. It says that because here we're using backwards differences, so we need to think that the array indices cannot start from the first element, for we cannot go, we don't have any element to the left, so we have to start from the element after. And another peculiarity with Python is you have arrays starting from 0. It doesn't start from 1 as we used in MATLAB, and this is something that is a source of irritation for a newbie, for one who is a new beginner in this type of programming. So here we are telling that the the first array index runs not from the zeros element, but from the first onward, and so is for the y element, because we're using backward differences. And even more surprisingly, the -1 actually is alluding to the last element into the array. So this takes a little of getting used to. So I definitely would recommend you to work through these examples, which can introduce you very fast to scientific Python and numerical Python, because what you always find in the tutorials is maybe more relevant for people doing programming, and not necessarily for those who will write lots of loops and solve numerical equations. So now I wanted to show you there are several equations which are being used in this introductory course, these 12 steps to Navier-Stokes. So all of them I'm very much recommending. Poisson's equation and Navier-Stokes for 2D in a box, and finally a channel flow. I will not go through this step by step because it will take very much time, but I would like to encourage you to look at them and download them and have them for your future use. Maybe you one day will learn Python if you haven't learned it before, or maybe you want to refresh your fluid dynamics course when you want to incorporate some modeling. So if you want to look how you can produce the last pages of the presentation, this McCormack scheme for 2D. This is how it may look in Python. I made it in this straightforward notation with indices because it's so easy to translate from the formulas in a presentation into the code. And this one I have run only with very few points, and it is in this initial condition and a very, very coarse grid of density after like 10 steps or so with very, very coarse resolution. The reason for this is like my first attempt to write it, so I have not optimized the time steps, and as you see, it's very sensible if you try to change the number of time steps in the x and y direction, you get very fast, you come into a region with divergence. But the skeleton of the program, that should be okay, it should be all right, it can be reused. So you are very welcome to copy it, download it, but of course I'm warning you that there might be some bug somewhere. So these bugs are all mine. So this is how it let us look at what is happening. First, we are defining all these constant and time steps, and this necessarily the grid minimum grid Reynolds number as defined, all the matrices to hold our momentum, P for predictor, C for corrector. For momentum is density multiplied with velocity, define them all. And first we have to put initial conditions, only flat function, flat density, and then we start our time loop. And starting with boundary conditions and producing predictor step for density and momentum. So it is actually the expressions which you have seen simply coded as they are, and I'm using this inefficient notation for the sake of clarity because you can easily identify all the indices. But if you want to make this code to run faster and optimize it, then I would suggest to change to this notation when dropping the loops and instead putting in the boundaries for i's and j's inside this parenthesis. And so we're updating velocity for all nodes as we have to do, dividing the momentum by density, and we finding velocities and putting all this into the corrector step, which looks like this, directly translated into Python. So if you want to explore this, it is available for you, and you are of course free to use it as much as you want, either in your courses or in your education. And absolutely, I can modify it. So all of this is placed in this GitHub repository, which you can access if you register there. So you can download and share as much as you want. So this is mostly what I wanted to talk about this today. I see we still have some time. So maybe somebody has their own experiences with using Python for calculations, which you can share. So, or have any questions, you are welcome to discuss now.
Thank you very much. Thank you. So, dear participants, we could discuss your experience, how Viktoria said.
Interesting to know which are the prevalent programming languages that you are using.
Actually, yes.
Many are already using Python, and how many are using packages like like StarCCM plus? How many are actually coding, hard coding numerical methods? It would be interesting to know your experiences in teaching.
So now I tried to create the question in Zoom. Okay. And 1 second, please.
Okay, you can write up into your chat.
Yeah. That's what I want. Okay, okay, without okay, without interview, I only write the question.
There are some of you who are still use MATLAB for working projects, or Octave. Octave I have never tried. So MATLAB is something which you are using actively, and I see Atlet and ANSYS CFX Python for post-processing. So I see that Python is used not for programming, but for treating data which you want to plot or post-process or do something. Okay, so not for coding. MATLAB for numerical, yes. Use Python code to plot, fantastic. Multi-physics research and MATLAB and C++ and C, yes. So, okay, so it seems that MATLAB is actually still quite prevalent. Fortran and C++, yes, Fortran. Yes,
we use Python too and Fortran too. Yes, I agree. So MATLAB.
So the majority is actually MATLAB or
MATLAB or Python, I think. Yes.
Or Python, yes. So that's actually quite a popular programming language to be using.
Being used in MATLAB for most of the time.
Do you do teaching?
Yes, guys, please answer the questions. And maybe as a question for this, I think it's very detailed, so that people, participants, try to understand all of this information. So
I hope it is some useful tricks which you can do, and especially those of you who are doing undergraduate teaching, a bachelor or master's, you may find it useful, some of those links, because as you know, Oh, there came interesting suggestion. I just finished talking, so I hope that you can do this, use some of this directly, as long as you use references to this this beautiful course made by Lorena Barba. I was actually quite impressed because you learn lots of things very fast, and especially for those of us who never had really formal training in programming. We're just scientists or physicists or physics educators, and we have an idea what a loop is, and we want to start writing code very fast without like spending months learning the whole syntax of the language. It's often too much, it's overwhelming. So I think it's a very good as crash start. And as I told you, if you register on GitHub, you can copy all those files and play with them as you want. And then there is a this was useful comment. I have a question. It seems that there are lots of loops on your notebook. Yes, there are, especially in the beginning. It was when I was only learning and I wanted to translate directly from the formula and into the loop, because that's what I know. It's a MATLAB thinking, and I thought, okay, I have to loop from every time step that we have to do that anyway, and then have to loop from all x and y values. And this was very easy because it's like you see your equation directly, and you're feeling that you're having an insight in what is going on. But of course, it is very clumsy way to do it. It is time inefficient. So if you want to do really big equation and discretize it finally, not coarsely, but finally, it will not work. And then I have to do this this notation which simplifies it, because here there should be two loops. You see there are two indices. This is for x and this is for y. So instead of writing two loops, it's hidden into this formality, which says that the all in x indices, all those i's in the formulas, they go from the first element, not zeros, but the first, and they stop at the last. And so for the j's and so on. So I'm kind of removing two loops using this notation. So, but there is also Cython. I have not heard about this. So if you have good tips, I am grateful to hear this. Maybe there is a link or something which can be done to use it, because I will be happy to use it in my numerics course to make a better course. Yes, and there is also a Python for data wrangling, extraction, and MATLAB for post-processing, easier to quickly learn things. Yes, I do agree. I tend to agree that MATLAB is easier because it is written with physicists and mathematicians in mind and not programmers, because that's what you encounter when you want to learn things. You go to Google, of course, and you write Python tutorial. And when it comes, fantastic big tutorial, but it is for people who do programming, who do informatics. And I don't want to read all those chapters. I want to go to see how to make a loop because I want to solve Euler equation or McCormack or yes. So it's sometimes it's you think that the threshold is high. So that's why I was so happy when I discovered this 12 steps to Navier-Stokes. So check it out, really. It takes you right into what you want to do and kind of leapfrogs the very detailed informatics focused thing, so which I find very, very good. Yes, Python and MATLAB is the most used in schools. In Norway, unfortunately, so far, we have not discovered Python yet. So a few individuals do it, but it's not been taken as part of the curriculum, which I really hope will be. Mm-hmm. Yes, and there is also a question of speed I see here. Yes, as I understand that inside all those Python libraries, which are being used, somewhere deep inside, when you want to diagonalize a matrix or do stuff with it, much more advanced than this tiny code which I have told you, showed you. And deep inside it, there are Fortran routines buried for matrix diagonalization, and It can be it can be fast, but it's not because the Python is fast, but because the routines it uses are fast.
Yes, and yeah, sorry.
All our code is Fortran programmed. Yes, this is from Luis Felipe. So Fortran is still being used, and it's actually very logical because as I understand, not being a programmer myself, that the more structure there is built on a language to make it user-friendly, the slower it becomes. So somewhere when you want to do really fast things in numerics, somewhere deep inside, they must be buried Fortran 70 routine or something, but you never get to see it.
Yes, and I agree about the reactor codes that are Fortran programmed, but I think it's for example, processing results. It's more useful use Fortran or Python, for example.
Maybe because there are not so many people actually learning Fortran anymore. So, and there is a little danger in that because they come to a point that nobody knows what's inside the deep black box. So, but somehow I hope that such a basic, humble approach that I have shown you today, like going back to basics, it can be a good idea. Maybe if you are not using it in your research, because what you're going to look at now, you will have very advanced examples now because you will learn multi-physics and star CCM plus, and you will see it very complex geometries and this kind of stuff. And you will draw domain and you will put boundary conditions, but you will never go inside the black box and you will never see what is going on because they're using finite element where they are the mesh are made of small rectangles or maybe the volume elements like prisms and these pyramids and this kind of stuff. You will never get inside the code. You will not see how they are matching these indices because it's too complex. And here you actually see everything. So I think before one does very, very advanced thing, it's okay to sometimes look down to earth and learn basic. Yes, simulation data. Structured data based on meshes created with mesh grid, who is better to reshape the matrix data if possible. Post-processing the simulation data. I haven't actually tried it, but I guess if you do this equation solver scripts directly to structured data, I'm not an expert, so I think it is possible because you can choose, for example, you can make a choice of how much data you are presenting. You don't need to plot everything. So it must be possible, just like in MATLAB, to selectively take part of the data, like every 10th or something, and plot them. So I think you can probably find routines for that too, but I'm afraid to answer because I haven't done it. And implementing Python code for undergraduate level nuclear engineering. What do you think is the best module to start with for nuclear engineering? I'm not sure. Maybe some here have suggestions. How do you start? It depends on what you want to do, I guess. What do you want to write the code right from beginning ab initio, or do you want to find something which is already produced and modified it?
Maybe for nuclear engineering to try to write the program about the nuclear transport, only one neutron, for example.
Probably possible if it's simply equations, as long as you can formulate whatever you want as a differential equation, and actually any choice would do. It depends on how detailed you want to model it. Because here we are looking at rather simple domains. You see, it was a square box and there was a square channel running. So it's simple domains could just sit down and write it, but complicated domain, then maybe there is a ready-made package in Python, and I would be surprised if there isn't a package somewhere already like modified for your use.
Processing, yes, MATLAB is a lot of stuff. The last one comments about C++, Fortran, Python, and MATLAB. Yes, I need to. Yeah.
Yes, that's also an impression I had before, that Python in itself, it's not fast. It's only fast if it utilizes some package with Fortran inside. So it is good for, I guess, for post-processing, all kind of other programming than scientific programming, and for illustration purposes. Because as you can see, it's a very low threshold to just log on the internet, register with this Jupyter book, notebook, or any other book. There are several. It's just one of them which I found very useful and easy to start with. And off you go, and you don't actually need to waste $1, 1 krona, or 1 ruble on anything, and off you go and learn programming. So I think for students, bachelor students, and even master students, it is a great idea and a good starter into the world of numerical modeling before you go to really heavy packages. So that was kind of the point of my presentation today, is to like take very basic things and hopefully give you some interesting things you want to try out for yourself, or maybe for your students if you are doing a course on fluid mechanics or numerical methods and want to show how to solve equations which you cannot solve with pen and pencil. And